Okay, I am making this video as kind of a backup plan just in case we didn't quite finish our notes over 3.5 on Tuesday in class. I'm going to start on about page 5 here on number 23. So if we got past that in class, then just kind of fast forward, skip over to where we left off. But I'm doing this as just kind of a backup plan in case we didn't quite finish those notes. All right, so remember, a vertical asymptote is a little imaginary vertical line that the graph cannot cross. Okay? A horizontal asymptote for a rational function is a horizontal line, and typically it's more talking about in behavior. So way out here on the right-hand side is the graph maybe approaching it from above or from below. And way out here on the left-hand side, maybe the graph is approaching that horizontal asymptote from either above or below. But unlike a vertical asymptote, remember a vertical asymptote, the graph absolutely cannot cross. Okay, it will only approach it, it will never cross it. But on a horizontal asymptote, the graph could cross it. Okay, so for instance, if we look at this one right here, the exponents are tied, so an x squared and x squared, so that's a COCO. So we know there will be a horizontal asymptote at the ratio of these coefficients 2 over 1. So there will be a horizontal asymptote at y equals 2. And sure enough, if I graph these guys, so I turn on the 2x squared minus 4 over x squared minus 3 minus 4, and I draw a line at the horizontal line y equals 2, and I graph those two. There's our rational function. And here goes our horizontal asymptote. And sure enough, on the far left, it looks like the graph is approaching the horizontal line y equals 2. On the far right, the graph looks like it's approaching the horizontal line y equals 2. But right here in the middle, the graph crosses that horizontal asymptote. Well, we said a graph can never cross a vertical, but it could cross a horizontal. So here's a case where it does. So if you are, and of course we have a graph right here, we can look at it, we can see that it crosses, but sometimes people would like to know, hey, is it going to cross the horizontal asymptote without having to graph it? Or if it does cross, where will that cross occur? So once we know that there's a horizontal asymptote at y equals 2, what you can do is you can say, hey, if the graph crosses the horizontal asymptote, which ours did, okay, we would like to know the exact ordered pair of that location. Well, we know that the y value of that point will have to be 2 because the graph was crossing it at 2. So we can say, hey, when does the y value equal 2? And we'll put 2 in for y here. So 2 equals 2x squared minus 4 over x squared minus 3x minus 4, and we just try to solve that equation. And if it has a solution, then we know, hey, when x equals whatever number that is, that's the place where it touches the horizontal asymptote. If we end up in a situation where there's not a solution to this equation, then we would know, oh, the graph must not touch the horizontal asymptote. All right, so let me show you what that would look like. If I want to solve this equation, I'm going to multiply both sides by x squared minus 3x minus 4. So on the right, I'll have 2x squared minus 4. On the left, I distribute the 2 through that denominator that I multiplied through. So 2x squared minus 6x minus 8. Both the x squared, the negative 3x, and negative 4, they all got multiplied by 2. So now I've got a nice quadratic equation here. I want to get everything on one side so it can be set equal to 0. So I'm going to subtract my 2x squared from both sides. And look at that. The x squareds cancel on both sides and leave negative 6x minus 8 equals negative 4. Well, now I notice, ooh, this is just a linear equation. It just has a single x. And I can solve that equation. So I'm going to add 8 to both sides. So negative 6x equals 4. Divide both sides by negative 6. And x equals negative 4 6, which is negative 2/3. So the point where this graph will cross the horizontal asymptote is at the point negative 2/3 2, okay, which is about where it looks like on that graph right there, okay? All right, another thing that happens sometimes with asymptotes, we've looked at several with vertical asymptotes and horizontal asymptotes. Another type of asymptote that we sometimes see, not always, but sometimes, is a slant asymptote. And let me show you an example of what that would look like. Okay, if I just graph this one right here, the x squared plus 1 over x minus 1. We know there's a vertical asymptote at positive 1 because that makes the denominator 0. I'm just going to look at the graph here and point something out. Sure enough, right here at x equals 1, there's a vertical asymptote, a vertical line that the graph does not cross. But it also looks almost like there's a slanted line right here that the graph appears to cross, but maybe never quite touches right there. And that is what we call a slant asymptote. Now notice, not all rational functions have slant asymptotes. In fact, slant asymptotes only exist if the degree of the numerator is exactly 1 more than the degree of the denominator. I like to say that as it's a botan by 1. So if the exponent is bigger on top, there's no horizontal asymptotes. Big on top, none for the horizontal. But if it's bigger by 1, there is a slant asymptote. So if you'll look at these two examples right here, do you agree that the exponent on top here is a 2, on the bottom is a 1, so it's a big on top by 1. And on this one right here, the exponent on the top is 2, on the bottom is 1. It also is a botan by 1. Big exponent on top by exactly 1. If it's bigger by 2 or 3 or 4, you will not have a slant asymptote. It has to be bigger by exactly 1. So this one will have, both of these will have slant asymptotes. The way to find them is to divide the top by the bottom. So in other words, to take x squared plus 1 divided by x minus 1. Of course, if I wanted to do long division, I need to put in my 0x in the middle. Since this is a candidate for synthetic, I'm just going to do that. I'm going to do synthetic division. And so since I'm dividing by x minus 1, positive 1 goes in the box. I write out my coefficients, 1 for the x squared, 0 for the plain x, 1 for the constant at the end, and I finish up my synthetic division. Okay. When you do that, whatever your remainder is, you can ignore. We do not care about that remainder, but this 1 and 1 right here stands for y equals 1x plus 1, and the slant asymptote will be at y equals x plus 1. So let me show you that. If I go back to this equation and I graph y equals x plus 1, I turn that on. Notice on my graph, there was my rational function. Here goes the line y equals x plus 1, and look at that. Sure enough, that looks like the perfect line for the graph to get really close to but never quite touch. Okay? I can do the same thing here. There's a big exponent on top. It's a bigger by 1. So there's no horizontal because it's big on top. It's a botan. But because it's 1 bigger, there is a slant asymptote. So I put my 2 in the box. 2, negative 5, negative 3 are my coefficients. Complete my synthetic division. Don't care about the remainder. I can ignore it, but my slant asymptote will be y equals 2x minus 1. And if I graphed this original rational and I graphed this linear equation right here, you would see, oh yeah, look at that. It's a good slant asymptote. Okay. All right, a few more examples here. Notice on these guys, they've just given us rational functions, and they ask us to find all the asymptotes, the vertical, the horizontal, and slant. Keep in mind, some of these functions may have all of them. Well, you can't probably have all. You can't have both a horizontal and a slant. You could have one or the other. Or maybe there's, not a vertical or not a slant or whichever one. So let's just kind of go through and see. I like to start out with my denominator, x squared minus 4. What would make that equal 0? Since that will factor to x plus 2, x minus 2. Then if x equals negative 2 or if x equals positive 2, both of those numbers are kicked out of my domain. And I just need to see if they cancel. Notice there's an x minus 2 on the top and an x minus 2 on the bottom. So although positive 2 is canceled from my domain, there's not a vertical asymptote at positive 2. That's where there's a hole. There's a hole at x equals 2, but not a vertical asymptote. The vertical asymptote occurs at the values that did not get canceled. So there's a vertical asymptote at x equals negative 2. Make sure we put the x equals, because that's what gives people our clue on whether we're doing vertical or horizontals, whether you have an x or a y. So there's a vertical asymptote at x equals negative 2. Horizontal asymptotes talk about end behavior. So I'm going to look for Bobo, Bot, and Coco. Looks like the big exponent's on the bottom here. So this is a Bobo, big exponent on the bottom. So the last O in Bobo is for 0. So y equals 0 is our horizontal asymptote. And remember, slants only happen when it's a bottom by 1. Since there's not a big exponent on top, by 1, there's not going to be a slant. And of course, you could graph these in your calculator and verify that we are getting the correct asymptotes. Okay? All right, this one right here, let's take our denominator, 2x squared plus 2, and set it to 0. It's a quadratic, so you know there's going to be 2 answers. You could try to factor it. You could do quadratic formula, or since I don't have the b term, there's just the a term and the c, I'm actually going to try to just solve it by isolating my x. So bring the 2 over, so there's negative 2, divide by 2, so x squared is negative 1, and take the square root, and of course if you try to take the square root of a negative 1, you're going to get positive and negative I. Those are imaginary numbers, so that means there's not a number that would make this denominator equal 0. Since there's nothing to make the denominator equal 0, the domain is all real numbers. Nothing gets kicked out. If nothing gets kicked out, we can't have any holes, we can't have any vertical asymptotes. So there's no vertical asymptotes. Horizontal asymptotes, we'll use Bobo, Bot, and Coco. This one's a Coco. Exponents are the same, 2 and 2. So that means our horizontal asymptote is going to be the ratio of those lead coefficients. So our lead coefficient here is 3. On the bottom it's 2. So y equals 3 over 2 is your horizontal asymptote. And remember, slants and horizontal asymptotes can't both happen at the same time. Slants only happen when it's bottom by 1, and this is not. So there is no slant asymptote. Okay, 28 here. We need to factor the top to see if anything cancels. Okay, this top may factor, but I don't think it's going to factor to an x minus 3, because the only way to get the 1 at the end would be if we had 1 and 1. So we're not going to be able to factor it to get an x minus 3. So nothing's going to cancel. All right, so I just want to see what makes that denominator 0. What would make the denominator equal 0, and that's 3. Since nothing canceled with the top, that means that 3 is where there's a vertical asymptote. So vertical asymptote at x equals 3. Horizontal asymptotes are about end behavior, so we're going to look at Bobo, Bot, and Coco. It's a big on top, okay? So if there's a big on top, the n in bottom stands for none. So there's not a horizontal, there's none. It is a bottom by 1. The exponent on top is 1 bigger. That means we can do some division to get the slant asymptote. So I'm going to divide 5x squared minus 7x plus 1, divide by x minus 3. I can do that with synthetic, so 3 in the box. 5, negative 7, and 1. I'm going to do my synthetic here. We ignore that remainder. So our slant asymptote will be y equals 5x plus 8. Okay? And then our last one here of this example, what would make the denominator equal 0? The denominator would equal 0 if x equals 3. So that means there is a vertical asymptote at x equals 3. Again, I should check and make sure that x minus 3 wouldn't cancel with anything in the top if we factored, but I know by having that 8 at the end that there's not going to be any factoring to leave an x minus 3, so I didn't worry about trying to factor it too much. Horizontal asymptotes occur when we have a big on top. So this is horizontal asymptotes when we have a big on bottom is 0, or when their ratio of the lead coefficients, when the ratio of the coefficients, if your exponents are the same. This is not. This is a bottom. Big exponent is on top, so there is not a horizontal. Since it's big on top by 1, this exponent's a 2 and this exponent's a 1, there will be a slant. So I'm going to do my synthetic division. Remainder is 2, don't care about that. But y equals 2x minus 2 will be our slant asymptote. Again, you could graph all of these in your calculator just to verify that it's all correct. Okay? And last, we're going to look at an application of these rational functions. Okay, a real-world scenario where rational functions come into play. This particular example we're going to look at is a business example. Remember, we've talked about cost functions before, how if you own a business, there's two types of cost. There's fixed cost, which are flat fees that you pay, probably like rent on your building or insurance, things like that are flat fees that you probably pay. And then your variable cost. Variable costs are costs that vary depending on how many items you produce. Would be a good example of that. So if you're selling something, you're producing and selling something, maybe you bake cakes at a bakery or something, and each cake costs you $5 to make for materials, then your variable cost would be $5 per cake. The fixed cost would be the rent on your a storefront or the equipment that you had to buy, those types of things. Okay? All right. Average cost is just what it sounds like. Take all the cost, all the money that you spend, and average it out by dividing by how many units you made. So we take that fixed cost plus our variable cost, the total amount of money we spent, we divide by how many items we made, and that's our average cost, how much we spent per unit. Okay? So an example here. Suppose a company manufactures robotic exoskeletons, whatever those are, and they have a fixed monthly cost of $1 million. That means every month they have to pay $1 million in cost for probably rent on their building, maybe to pay their employees, different things like that. And then they pay $5,000 to produce each robotic system. That $5,000 is probably for their raw materials that they had to purchase. Okay? So our cost function, our C of X, will be $1 million, that $1 million they paid up front, plus $5,000 times however many skeletons they made. Okay? So in other words, if they built 25 skeletons, we could put 25 for X, work this out, and that would be the total cost that they spent that month. Okay? The average cost, note the symbol for average cost still has a C, but it's got a little line on top. Those of you that have taken AP Stats know that when you put the line on top, that means average or mean. Okay? So our average cost for each skeleton is however much we spent. So $1 million plus 5,000 times how many we made. That's how much we spent, divided by however many we made, which we're going to use X for that. Okay? So that's our average cost function. Now they want us to find and interpret average cost of 1,000, average cost of 10,000, average cost of 100,000. Okay, so here's what that means. Average cost of 1,000. They want you to take that average cost function, but instead of putting X, I'm going to put 1,000. They're telling me to plug in 1,000 for X. Instead of the X on the bottom, instead of that, I'm going to put 1,000. So in other words, if you make 1,000 units, what is your average cost per unit? Okay, so I'm going to spend that $1 million plus 5,000 times 1,000. So I'm going to have spent, what is it, $6 million divided by the 1,000 units I made. And I get 6,000. Okay, so what that means is it cost an average of $6,000 per system to produce 1,000 systems. So if you're going to make 1,000 robots, you're going to spend your $1 million plus 5,000 times 1,000. Each of those 1,000 systems cost $5,000. So you'll have spent a total of $6 million. But you spent $6 million to build 1,000. So when you divide that out, that comes out to $6,000. So you're spending an average of $6,000 per system if you make 1,000. Now, average cost of 10,000 is what's the average cost? How much does it cost per unit if you build 10,000? So notice you still have your $1 million that you're spending times 5,000, or sorry, plus 5,000 times 10,000. That's your total cost divided by the 10,000 units you made. And then you divide by, like I said, the 10,000 units that you made, and you get 5,100. That means if you build 10,000 units, the average cost of each one is 5,100. Well, why is it cheaper per unit to build 10,000 than to build 1,000? Well, it was still $5,000 per unit, but now that $1 million, instead of that $1 million being split among 1,000 units that you made, that $1 million is being split among 10,000. So it's being divided amongst more items. So that lowers the price per unit. Okay? That's exactly why in many cases businesses prefer to make a lot of something, because they can get that average cost down. The rent has to be paid on the building regardless of how many they make. So you might as well make a lot so that your cost per unit can come down. We did 100,000. Notice that that $1 million up front is now being divided by 100,000 units. So when you work it out that way, it comes out to $5,010. So notice by making 100,000 units, our cost per system has gone down even more. Okay? Now, here's something that we have to think about though. Does this graph have a horizontal asymptote, and what does it have to do with our average cost function? Okay, so notice, if I were to make 1 million units, that would come after 100,000, right? It'd be 1 million, or 2 million, or 10 million, or 80 million, or a trillion, or whatever. If I create a huge amount of units, this average cost should keep going down. But there's a limit to how far down it can go, okay? It can only go down so far. And the farthest it will go down is wherever your horizontal asymptote is. So let's take a look at this average cost function again. Notice that it was $1 million plus 5,000 times however many we built, divided by however many you built, divided by x. Notice this was a rational function. I hadn't really mentioned it, but it is. In fact, it would be a COCO, right? The coefficients on this x, the exponent on this x, the exponent is 1. On this x, the exponent is 1. So their exponents are the same, so we use our coefficients. The coefficient on top, coefficient in front of x is 5,000. Coefficient in front of this x on the bottom is 1. 5,000 over 1 is 5,000. That means there is a horizontal asymptote at y equals 5,000. Well, what does that have to do with our average cost function? That means if you built more and more and more systems, you went from, 1,000 to 10,000 to 100,000 to 1 million to 1 billion to 1 trillion, the horizontal asymptote would approach 5,000. That means the more systems you build, okay, the more systems you build, the closer your average cost will get to $5,000. It will approach $5,000. It won't ever quite get there, and it certainly won't dip below 5,000. Now, that kind of makes sense even if you weren't thinking about rational functions. Remember how we had to pay $5,000 for each system? So the lowest your cost could ever get would be just barely above 5,000, even if that $1 million had to be paid. So even if you split that $1 million among 10 million units, the lowest it could ever get is basically a penny. So your $5,000 plus, a penny or something for that particular item's share of the $1 million. Okay? So the horizontal asymptote would be at y equals 5,000, and that represents what your cost will approach, but it can never go below that.